In session number 1, I wish to address the title, which is often asked by people across the pale blue dot, as Carl Sagan described our planet, and that is our universe. Is it an accident or is it design? And the answer to that fundamental question determines how you approach your lifestyle, how you approach your very thought processes within this cosmos. Am I simply an accident, a zero? Or is there design, a purpose behind the grand scheme of things? This is what I shall be exploring this morning. There are 3 fundamental questions which are at the heart of this presentation. These 3 questions, ladies and gentlemen, were actually asked when Professor Stephen Hawking, one of the world's greatest scientists of all time, and myself were interacting some years ago. And Professor Hawking asked me 3 questions, which kept me riveted, seated, as it were, on the very edge of my chair. And the questions were thus: why are we here? Asked Stephen Hawking. Where did we come from? And where are we going? And underpinning the whole theme of our universe, accident or design, are these 3 questions, which I repeat. Why are we here? Where did we come from? What are our roots? What are our roots? And where are we going? To many, life is a nightmare. And I couldn't find any better little verse here, as it were, part of a song, than this one from I'm Just a Kid, the group Simple Plan. I'm just a kid. Life is a nightmare. I'm just a kid. I know that it is not fair. And then comes the line which underscores the blackness of it all, almost the annihilation feeling by Nietzsche and others. Nobody cares. Of course, I'm alone in the world. Before you came here today, you might have just thought that sins belong in terms of Scripture. But I've learned, as an astronomer, that there are scientific sins. And I'll allow you to read this quote for yourselves, but I wish to elucidate the first sentence. Written by Sir Fred Hoyle, a truly legendary astrophysicist, and Chandra Wickramasinghe. To involve purpose, and I quote, is in the eyes of biologists the ultimate scientific sin. To invoke purpose, not only in astronomy, but to invoke purpose in this cosmos, ladies and gentlemen, to this very microsecond, is a sin. Please remember that. Don't let that thought go. To invoke purpose in any theory whatsoever is, in the eyes of biologists or cosmologists, or whatever the domain of study might be, the ultimate scientific sin. But then Sir Fred goes on to say that there's a revulsion. Folk feel like throwing up when you mention purpose. They need Valoid. Even folk who suffer from nausea say that folk who invoke purpose need Valoid and are very nauseous. To invoke purpose creates a revulsion. And so before I set the scene, as far as our universe, accident, or design is concerned, I need to take you on a journey through space and time. That journey obviously will start on the planet on which you and I live, move, and have our being, the planet Earth. And then we shall begin our cosmic journey, just so that I've set a foundational stone to the story which is about to unfold. Undoubtedly, that planet which I adore the most, that planet which I find so awesome, is the planet Saturn. Saturn with its glorious system of rings. Saturn which beckons to the telescopic eye that possibly there is a purpose and that there is a designer behind such grandeur, behind such splendor, and behind such beauty. And so we come to Saturn at different periods in its orbit. And it is a vast, awesome sight to behold. But Saturn is only the start of our journey into cosmic space and into cosmic time. Our closest star, and these are real photographs, ladies and gentlemen, not animations or drawings. Here we see our writhing, seething, closest star, the Sun. The temperature at the center of the Sun is 16 million degrees centigrade, which means that you can bake, fry, and boil simultaneously. The Sun is a woman's dream. It continuously loses weight. The Sun becomes lighter by 4 million tons every second, perhaps slightly more than is on your Weight Watchers, or way less target program. But here is real live imagery of a flame erupting on the Sun called the solar prominence. And again, this is a real live color footage. We are not using any animations whatsoever. And it shows you just the incredible extent of one flame on the Sun, one solar prominence, compared to the size of the Earth. But then the Earth, compared to the size of the Sun and the other planets, all of them put together, the Earth especially, is dwarfed into insignificance. Just look at the scale size here of the Earth, juxtaposed against even Jupiter and Saturn, and then against the limb of the Sun towards the left-hand sector of your screen. The Earth, so small, are we indeed simply an accident in this vast cosmos? The Earth compared to the Sun is minute, but look at the Sun compared to other stars, stars perhaps suffering from stellar obesity. And what I show you over here is the size of Arcturus and the size of the Sun juxtaposed against each other. I am very grateful. My neurophysiological processes did a little leap when someone in the audience, at least one, said, "Whew," they gasped, they were alive, they feel the vibrance of the size of Arcturus compared to the Sun, where the Earth isn't even but a pixel. Then we compare Arcturus to some of the other stars, not ones which visit, say, one of the famous hamburger stores and are really obese. But stellar obesity on its grandest scale, Beetlejuice, don't say Beetlejuice, you'll sound illiterate, Beetlejuice and Antares. Too many people come to me and they say, I've just seen Beetlejuice. And say, you need a psychiatric ward. You ain't seen no juice. You need Beetlejuice and Antares. But what I wish to stress is on this scale, the sun is a pixel. The sun is a pixel. If you don't know what a pixel is, ask your son. The sun is a pixel. What's the earth? Microscopic. And so, we look at 100,000 million stars on the big screen. The Milky Way galaxy, 100,000 million stars. If you had to count, ladies and gentlemen, 1 star per second on this big screen, it would take you 2,500 years to count them all. The Milky Way, the vastness of the Milky Way, different views of the Milky Way, reveals an arch-like structure. And within that arc-like structure are dark bands, which I've studied for many, many years. Dark bands seen all over, sprawled over the vast screens. And this plethora of dark stuff is the stuff that I study, cosmic dust. These clouds of cosmic dust, just one of them, is perhaps larger than you might think. Here is one column of cosmic dust which spans nearly 10 light years across. That means that light, if I took a little torch beam and flicked it on the left-hand side of the screen, light traveling at 300,000 kilometers per second in vacuum would take nearly 10 years to reach the right-hand sector of my screen. If that doesn't excite you, you're dead. And so these columns of cosmic dust are really awesome. This is a photograph which I personally took in the Atacama Desert in Chile, showing you a juxtaposition again of stars and again of baby stars being born with the most glorious sets of colors to which the naked eye is simply not sensitive to. May I also draw your attention to the fact that this is around a 4-hour exposure. The birthplace of stars are too beautiful to behold, as you can see before you. Messier 42 in the constellation of Orion, a stellar birthplace where stars are being born as you are drawing your very breath. And as I've studied and as I've researched these columns of dust over the years, some of our research has been featured twice on the cover of Nature. And that is an awesome calling and a secret. And I'll unfold the secret in next week's session. But there's an incredible secret to the slide which I shall elucidate next time. In our journey in cosmic space and in cosmic time, we start leaving our solar system. We start moving to the Andromeda Spiral Galaxy. Light from this galaxy, seen here in the infrared through the eyes of the orbiting Spitzer Space Telescope. I had an embarrassing moment a while ago. Someone asked me when last I've been to the Hubble or Spitzer Space Telescope. Well, I happen to have an address in South Africa. I haven't yet been on a telescope orbiting the sun. But we forgive these people for their ignorance. And so, I'm really just kidding you, of course. I don't expect you to know that I'm not in orbit about the sun. But this is the Andromeda Spiral Galaxy in the infrared, and it's really just Absolutely stunning. So the building blocks of our universe are galaxies. Those are the building blocks. This is a building block of a galaxy, NGC 5236, Messier 83, and again, it's around 100,000 light years across. So if you flick the torchlight on the left-hand sector of the screen, the light would only reach the right-hand sector of the screen in around 100,000 years' time, traveling at a speed of 300,000 kilometers every second. And the building blocks of our universe are awesome, and no two are the same. You come across one building block upon another, like this one, NGC 5194-5, the Whirlpool Nebula, and it's just glorious. But within this are 100,000 million suns. But, and this is an incredible image, ladies and gentlemen, every little fuzzy dot that you see in this image is not a star but a galaxy. So every little dot, every little fuzz that you see here is not, by no means, is that a collection of stars. You're actually looking at a cluster of galaxies. But then perhaps one of the grandest slides I can ever bring you is this one. Every dot in this image is a galaxy. Around 100,000 light years across each one. So on this scale, you start saying, oi, they. Oi, they. Where do I belong in the grand scheme of things? Where am I going? Why am I here? Given the vastness of the cosmos. Now, there's something very important in all of this, and that is in astronomy, we're always looking back in time. When I look at the sun, I'm looking back just over 8 1/3 minutes in time. I'm always looking back in time because in astronomy, time, information takes time to travel. But many of my students have great difficulty with this concept. And many people on radio and television also have the greatest of difficulty with what we call look-back time. Information takes time to travel. Follow me. The date, January 1 of this year. Let's see what happens on January 1. On January 1, there's sexually active people in Johannesburg, and a baby's been born. In Josie. That's not hard to understand. A baby's been born in Johannesburg. On the same date, a baby's been born, and you can Google that structure if you don't know what it is. But a baby's been born in that city. Not only that, but a baby's been born in Moscow on that date. And a baby's been born in New York. So, 4 babies are born on the same date. But the important thing is, I don't have that information at hand. Why? Well, I want you to imagine this. On January the 1, we know the baby's born in Josie. So there's no complication with this example. But in March, the 28th of March, 2-3 months down the line, the baby's grown some. Some of my students have problems with some of these examples, but it's a normal process that in 2 or 3 months the baby grows. So in 2 or 3 months the baby's grown. The date is now March 2013, March, and a letter arrives dated January 1, 2013 from Paris. The letter arrives. So now my horizon of information is increased. Only in March, some months later, do I learn of an event which actually happened on January the 1. Now, I want you to imagine in your mind's eye a postal strike. I want you to think of the postal strikes we've had here and multiply that by 1,000,000 times. I mean, we call it a massive postal strike. Even folk who are accustomed to postal strikes would say that postal strike's astronomically chaotic. All right, so watch. Some time elapses, a lot of time, 2 years, massive postal strike. And in July 2015, a letter arrives. It's dated January 1, 2013. And it's news from Moscow. A baby is born in Moscow. But we're looking back in time, as it were. The news is taking time to travel. And the further the city, the longer it takes to travel. And finally, in December 2016, our baby in Johannesburg's grown up son, beautiful young girl, we get news of the baby born in New York. And that's the analogy in astronomy, is that as we look at all these galaxies, we're always looking back in time. Information takes time to travel. In astronomy, we're always looking back in time. So many years ago, I asked a student, how do you feel in this vast cosmos, given what I've told you? And he or she, I can't remember exactly what the sex of the person was, who drew this little diagram, but it's very profound. There's a little white dot, lower right of the screen, of the square. The square represents the cosmos. And this student feels like a zero, a nothing, in the vastness of space and of time. And the person who got it right was Bernard de Fontenelle. And he got it right, and I want to read it to you. Behold a universe so immense that I'm lost in it. I no longer know where I am. I am just nothing at all. Our world is terrifying in its insignificance. And that is the sort of feeling that modern man and modern woman have today, is that the universe is so incredibly large that they feel, this is interesting, they feel as if they are nothing at all. And so in this whole process is this: can we actually unmask God if there is one? Is it possible to scratch the scientific pages, as it were, and try and find evidence, if you like, of God's handiwork within the cosmos? Are we able to delineate? Are we able to truly unmask God? Now, you have to follow me carefully. There are four forces, four fundamental forces, which cement our universe together, if you like. These are called the electromagnetic force field, the weak nuclear force, the strong nuclear force, and the gravitational force field. Now, at this stage, you might say to me, David, please don't lose me. And so I won't. I've got lots of examples to help you. And when you're still struggling and dying from, when you still can't understand my examples, I'll repeat myself in Q&A time. And if you still don't follow them, you have to repeat the course. So we're going to look at two forces. We're not going to look at all four. We're going to look at the electromagnetic force, the gravitational force field, and then the ratios, and what they're responsible for. So this is a schematic. This is not a real image. This is a schematic of what? Gold. No. It's quite close. What's it a representation of? One atom. Pinch yourself. You are made of the stuff. Be sure you know what you are made of, ladies and gentlemen. This is an atom. What's at the center? The nucleus. Protons and neutrons. What are orbiting in those blue little orbits? Electrons. What's the charge of an electron? Positive or negative? That's right. Some say positive, but they fail the course. The charge on the electron is negative. The charge on the proton is positive. Now, let's imagine that we are at liberty to play with the value of the electromagnetic force field. Suppose we increase it. Does anyone know what will happen? If we make it any stronger, the negatively charged electrons start speaking, not of course like this, but start speaking to the positively charged protons. And they say, "Oh, thou proton, what a wonder thou art to behold! How thou beckonest me to draw strangely thither nigh unto thee." And they fuse to form a neutron. If the electromagnetic force field were higher, the negatively charged electrons would experience a wonderful romance in the atomic quantum world with the positively charged protons, and there'd be no atoms. There'd be no atoms. On the other hand, if you were to weaken the electromagnetic force field, there'd be no electrons in orbit about the nucleus. If you were to weaken that electromagnetic force field, the electrons would no longer be attracted to the nucleus, and there'd simply be a vast sea. Atoms would not exist. Now, one of the people who's looked at this very, very carefully is Sir Fred Hoyle. And before I elucidate that, let's just summarize what I've said. If you weaken the electromagnetic force, electrons not bound to their parent nuclei. If you strengthen the electromagnetic force field, there are no atoms. There'd be a universe of neutrons, and we wouldn't exist. So in the atom, there seems to be very interesting, intricate evidence for design. Now, how finely tuned is this ratio of forces? The electromagnetic force field to the gravitational force field. It's finely tuned, ladies and gentlemen, to 10 to the power 36. Now, I don't hear any gasps. I don't hear any oohs. I do not hear any ahs. I may as well be at a funeral parlor. Now, the reason there are no oohs and ahs is because you don't understand this. There's a lot I don't understand in your field. I mean, you start speaking to me about, what Vickers does so well on stage with singing and so on, and I'm totally lost. I mean, when I start singing, everyone leaves. So let me explain it to you. Let me unpack it. All right, let's imagine some guys, and they behind a machine gun. We tried to find some slides with ladies behind to be politically correct, but we couldn't find any with those hats. So we stuck to guys. I ask for pardon. And so there's this belt of bullets. Can you all see that belt of bullets? And now we're going to fill that belt up with different bullets before we start firing our gun. So got our belt, and we're going to fill it up with a vast number of bullets, and then we're going to give the belt a tug. We're going to just ask one of you guys or ladies to come forward figuratively and pull the belt randomly, and I ask you to stand in front of the gun, and I pull the trigger. All right? So we give this a random tug, and to help you on your way, let's use so many bullets. There are 100 there. I checked last night. But Neil did a great job of counting. And there are 100 bullets. So we're going to put in to the belt 100 bullets. And then what we're going to do is we're going to remove one bullet only, just one. My students might say to me, "Prof, where's the one you've removed?" So we've got it in red. Okay, so there's this belt with 99 bullets now. There are 100 holes. One is free. And what we do is we put them into our belt and we randomly pull the belt. And we just give it a random pull. And I say to you, stand in front of the gun and I'll pull the trigger. What should happen to you? If I pull the trigger, that's right, you should be dead. In fact, mors dood. Why? Well, if that doesn't kill you, you need help. So the chance in this experiment of remaining alive is 1 in 100. There's only 1 in 100 chance of the hole which is empty being orientated in the belt so that it's right at the top of the turret, so that when you pull your machine gun, you're alive. The odds against that happening are 1 in 100. That's called fine-tuning to 1 in 100. And the incredible thing about the atom is the atom is finely tuned not in 10 to the power 2, but to 10 to the power 36. What does that mean? That means that not only do you take 100 bullets, but you take so many bullets. That's a 1 followed by 36 zeros. Minus 1. Left 1 hole free. And somehow, somebody has seen to it that the only hole which will work to give rise to intelligent human-based life has orientated the machine gun so that when you pull the trigger, we are alive. That's the fine-tuning of 1 part in 10 to the 36. Is you, against all probability, you shouldn't be here today. The chances of you being here today, just based on this example alone, is 1 part in 10 to the power 36. We should not be here. Not only with regard to the electromagnetic force field, but if the gravitational force field were changed with respect to the electromagnetic force field, all stars would be blue, 50,000 degrees centigrade at the surface, bake, fry, and boil simultaneously, I guess. 50,000 degrees centigrade. If you were to decrease the value of the electromagnetic force field and the gravitational force field and the ratios thereof, all stars would be red. And in fact, if you reduce it too much, you don't get production of heavy elements at all. So, where are we heading? When you look at the atom, you realize that not all values are equally probable. This is astounding. Because if you say the universe is an accident, then all values would be equally probable. But the universe contains finely tuned forces in which and for which not all values are equally probable. That sentence alone starts taking the sting out of the angst of Bernard de Fontenelle. Now, instead of me saying this, allow Sir Fred Hoyle to say this. And I quote, "A common sense interpretation of the facts suggests that a superintendent has monkeyed with the physics, as well as chemistry and biology, and that there are no blind forces worth speaking about in nature." He continues, Sir Fred Hoyle does, "I do not believe that any scientist who examined the evidence could fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside or within stars." And so we stumble upon this notion of a superintendent, of someone designing, fine-tuning these incredible forces. If you want to summarize what Sir Fred is saying in a nutshell, it is well known that carbon is required to make physicists, said Professor Dick at Princeton. Well, you can paraphrase this and say, it is well known that carbon is required to make you. This is extraordinary, the fine-tuning within the atom. But there's more. In this incredible image from Paranal in Chile, a country where it is not Chile, you work with these incredible telescopes. And you see the arching Milky Way. And with these giant telescopes, we find that the universe is expanding, much like myself. So my students say to me, Prof. Block, I don't understand expansion. So I say, look at me. Look around me and draw the conclusion. I am here. So we represent our universe now, the baby universe, with a little balloon with galaxies. Then it grows. It gets inflated, if you like, but it grows. The universe is bigger. Then finally the balloon is even bigger. We live in an expanding universe. And the way that we discovered this is by means of the Doppler shift, which I'll go into in a moment. But very simply put, we find that the further a galaxy is from us, the greater is its redshift and the faster it moves. So here's a relatively nearby galaxy. Here's a galaxy moving with a greater speed away from us because it's farther away. And here's a very highly redshifted galaxy. See the calcium H and K lines in black. See the red arrow. Very distant galaxy moving away from us very quickly because it's so fast. This is proof of the fact that the universe is expanding, and we give great credit to both Lemaitre and Hubble for their pioneering work in this regard. But it all hinges on the Doppler effect. So the Doppler effect is simply something explained on the screen, that when you've got an observer and a source, when the source is moving toward you, the pitch increases, and when the source moves away from you, the pitch decreases. So just listen to a sound effect which you may never have heard in your lives before. The Doppler effect. Blowing the hood, car approaching the observer, increase in pitch. As the car recedes in the distance, the decrease in pitch is evident. I've been privileged to study galaxies through some of the world's most sophisticated telescopes ever designed. And every time we're in the control rooms of these incredible telescopes, and we see the starry Via Lactea, the Milky Way ahead of us, one cannot but think to Genesis chapter 1. But there seems to be a little problem here. In Genesis chapter 1, and the reason I'm bringing in Genesis now is I'm working within a Galilean framework. Galileo spoke of the book of Scripture and the book of nature as two separate books, but both having the same author. So I want to look at Genesis chapter 1, and in verse 3 we see, and God said, let there be light, and there was light. But then later on he goes and makes the stars. The question is, how can you have light before the stars or the sun is made? Astronomers sent up a very famous telescope with a very famous detector on it called COBE, C-O-B-E, the Cosmic Background Explorer. And it searched the entire sky for radiation which might enable us to have a peek at the very moment of creation of our cosmos. And it sent back this image which rivets me. This is an image of a universe with no stars and no galaxies. This is a universe of pure light only. This is a universe showing you one of the first snapshots of our universe when it was birthed. And I have a lot more to tell you about that next week. But this is our universe, filled with light. How interesting that in the beginning there's light only, and only later on, ladies and gentlemen, do we start seeing the formation of galaxies. And we've sent up other spacecraft. Here is WMAP, showing you the same thing, a universe without stars. We've sent up the Planck telescope. And obviously the resolution improves with time, but the bottom line is that Scripture is beautifully affirmed. In the beginning, you need a universe of light only. Then later on, the universe grows, it expands. But how does it expand? At what rate? I need to unpack this. But there was a moment when a Nobel laureate and myself were chilling together. The Nobel laureate is on the right. His bank balance is much higher than mine. The Nobel Prize is not negligible. And we're both smiling, as is the custom when talking about cosmology. I am using my hands, as is a custom, both to pull up my pants and to express my passion. But what George Smoot said was very interesting. He said, if you're religious, now George Smoot was one of the designers of Kobe. He said, if you're religious, it's like looking at God, because there is a universe of pure light only. Now, the question I want to ask you is this. I've painted a picture of the universe so big you feel like a zero in it, as emphasized by Bernard de Fontenelle. But let me turn the question around now. How big must the universe be to contain you? How big must the universe be in order for it to be your home? Well, what are we made of? We're made of carbon-based stardust. We are made of the stuff cooked in the interiors of stars. And so, in order for that carbon-based stardust to exist, we need certain processes to unfold. What you're seeing on the large screen is an exploding star, Messier 1, the Crab Nebula in Taurus. And the way the star, what happens is, the star cooks the heavy elements, including, for example, you've got the carbon and then the heavy elements. And what's really happening here is that locked inside the star are these heavy elements, and they get released into space by means of supernova explosions. And so the process is this. Our universe gets bigger by 1 light year every year. So every moment that I'm talking to you, in 2010 compared to 2011, the universe grew in size by 1 light year. But there's a whole intricate story which unfolds as you look at this. First of all, for us to be here, we must have carbon. Well, where's carbon made? I've told you, carbon is manufactured in the interiors of stars. So you need stars. But before you have stars, you must have galaxies. The building blocks of our universe are galaxies, and they contain stars. So you need galaxies, you need stars, you need enough time for galaxies to form, enough time for stars to form, enough time for stars to explode, and then enough time for planets to form from this carbon-enriched material. And if you go through that calculation, which I won't do today, but you need around 12,000 million years for that process to be fully enacted. But remember that the universe is getting bigger by how much? 1 light year per year. So if you look at this little schematic, you need around 12,000 million years at the bottom of the screen for this to unfold. You have what's called the afterglow. the glow of the creation event. You have the dark ages. I'll speak about that much more next week. You have galaxies forming, planets forming, stars forming. And it all takes about 12 billion years until we are here today and we can live, move, and have our being. And so we see something very extraordinary. The universe must be 12,000 million light years across in order to contain me. Say it with me. The universe must be about 12,000 million light years across in order to contain me. Now say it with passion. The universe must be about 12,000 million light years across in order to contain me. Therefore, you are unique and irreplaceable. You couldn't live in a universe that was any smaller. That's the bottom line here. And so when we look at these galaxies, such as in the Hubble Deep Field, the time from these distant galaxies, and remember information takes time to travel, we're looking at around 12 billion years back in time. The light from these galaxies left these galaxies around 12 billion years ago. The photons have been traveling to Earth moment by moment. But you could not live in a universe that was any smaller. And I emphasize this. It was in quotes until somebody asked me who said this. And I realized it was me. So I've removed the quotes. The other day, one of South Africa's leading poets, T.T. Kluter, said, "Prof, I want to give you a quiz." I thought, oy vey. My usage of Afrikaans is so limited compared to T.T. Kluter, who's won the Hertzog Prize. And he said, "Prof, sit down and have some tea," which I did when invited to do so. And he said, "I want to read you a quote." Who said it? Well, I thought to myself, could it have been Einstein or Dirac, or went through some of the famous names? It was in a book, published in a book of poetry by T.T. Kluter. And he handed me the book, and to my absolute shame, it said by Professor David Block. I forgot I said it. And so I gave the quiz to my wife. She was standing in the kitchen, cooking supper, as is her wonderful custom. And I said, "Honey pie, I've been ashamed today. I've failed in a quiz given to me by the great T.T. Kluter. Honey, do you know whoever said these words?" And without one hesitation, while stirring the spaghetti bolognese, she said that was David Block. All right, fine-tuning in the atom. We've seen that very beautifully. What about this? The universe is expanding. But this is one of the most incredible features, which Stephen Hawking has studied so beautifully. The fine-tuning in blowing up the balloon of our universe, it's finely tuned to 1 part in 10 to the 55. You'd need a 1 followed by 55 zero bullets. Load the gun with all those bullets and keep one hole free. And someone's gently blown this balloon up so that the universe is here today. If the early universe expanded too slowly, gravity would become the overwhelming force and the universe would recollapse. If the universe expanded too fast, galaxies wouldn't form, there'd be no Milky Way or suns or stars, and there'd be no life. And the fine-tuning in the expansion rate of the universe is in 1 part to 10 to the 55. And so, the greatest of miracles is upon us. The greatest of miracles is that you are here. Say it with me. I am here. It's extraordinary. You shouldn't be here. Everything has worked together with regard to all the weak nuclear forces, the strong nuclear forces, the ratio of the electromagnetic force field to the gravitational force field. Everything has worked, including the rate at which the universe expands, finely tuned in 1 part to 10 to the 55, so that everyone you can see here is indeed here. And it takes the sting out of accidents and puts in the glory of design. It takes the sting out of the quote of Bernard de Fontenelle, that we are just a nothing in this vast cosmos. The universe has to be as big as it is to contain you, but much more. The universe has to expand at exactly the right rate in order for you to be here today. All right. So what's the devil's advocate? You always need here in cosmology someone to think of an argument to try and deflate what you are saying. Devil's advocates. They abound in my science. And they'll always try and just give you a little pinprick where you shouldn't have one. So, Stephen Hawking was very quick to understand that one of the bubbles, our universe, is incredibly finely tuned. He understood this. He understood this from the rate of expansion of the universe, from the fundamental forces operative within the universe. He understood that our universe, we shouldn't be here. He understood it. As the world's greatest scientist, greatest living scientist. So, what's the devil's advocate? Well, the devil's advocate goes like this. Well, Prof, you are a prof of applied math. I say yes. They say, well, Prof, muni warini. You're not special at all. You're not special. They say, let me continue. And they say this. They say, well, of course, we've got you. What you've said cannot be debunked. I've written books on this, prefaced by Nobel laureates. So, we're not talking here from an uneducated point of view. But the argument goes, well, there's this extraordinary bubble, our universe. But, Prof, there are zillions of other bubbles out there which don't contain life. Possibly don't contain. And so the argument goes that there's multiverses out there. But the interesting point about these multiverses, why is there such a push for the multiverse? Is it science, or is it because we are trying to get out of a very nasty corner here with regard to design? And I would argue, as does Martin Gardner, that multi-universe theories have an agenda. You might not know this, but I have seen this in play. I have read and interacted with some great minds in this regard. And I would say to you today at Il Grande at Monte Cassino that multi-universe theories are driven by an agenda. You can read what Martin Gardner says there, but I am firmly of the belief that multiverses takes you outside the domain of science because they are proposing universes whose existence is completely unobservable and furthermore untestable. Some great minds have echoed what I am saying. But I would like to just say that the devil's advocate to me fails abysmally because we are encountering again within this agenda the ultimate scientific sin. I have interacted over many years, I suppose since the early 1980s, with a professor at Harvard University. His name, Owen Gingerich. And it's a beautiful quote which I'd like to read here this morning. Dare a scientist believe in design? Dare a scientist believe in design? There is, I shall argue, no contradiction between holding a staunch belief in supernatural design and working as a creative scientist. And perhaps no one illustrates this point better than the 17th century astronomer Johannes Kepler. Unquote. A quote, ladies and gentlemen, penned at one of the top-ranked universities in the world, Harvard University. And so as I begin summing this up, where do we go? Well, I believe it's good for others to perhaps echo the story which I've been building upon today by Arno Penzias, who won the Nobel Prize in Physics. And I wrote to Professor Penzias to preface one of my books. And this appears in that book. And there are DVDs outside of that presentation. Astronomy leads us to a unique event. A universe which was created out of nothing. Creation ex nihilo. And delicately balanced, and you've heard the story unfolding, and delicately balanced to provide exactly the conditions required to support life. Professor Penzias continues, and I quote, "In the absence of an absurdly improbable accident, the observations of modern science seem to suggest an underlying, one might say, supernatural plan." And then he concludes by saying, in this lecture, Professor Bloch, oh, that's me. In this lecture, Professor Bloch offers you a unique opportunity to weigh the evidence for yourselves. But what struck me about his quote was the following, that in the absence of an absurdly improbable accident, the observations of modern science, ladies and gentlemen, seem to proclaim a message of a supernatural plan, which I unpacked in session 2. The awesomeness of the plan. In the absence of an absurdly improbable accident, the observations of modern science seem to suggest God. The observations of modern science seem to suggest God and his plan. But, Professor Penzias continues, as he would, there is no force upon you. There is no force upon my children to accept what I'm saying. You are a unique being, created in the image of God, I would assert. But the universe, I would assert, according to the evidence I've presented, is designed rather than accident. And so, why are we here? Where are we going? What are our roots? And as we look at this incredible image in space, the story ends on the person you. The story, ladies and gentlemen, ends thus. What is man that thou art mindful of him? Asked the psalmist. And the Son of Man, that you care for him. The universe, I would assert, is designed. The universe, I would assert, proclaims an eternal plan. The universe, I would assert, is impregnated with the most awesome set of fine-tunings you can ever imagine. Ladies and gentlemen, I thank you for your attention.